In an earlier video, we talked about the Gibbs free energy G and how we could derive it from taking the internal energy and subtracting T times S and adding P times V, and then we get this differential dG is equal to V dP minus S dt. Now, when we show this, however, this is not all of the ways in which dG can vary. So here we have dG, an infinitesimal change in Gibbs free energy, can be related to changes in pressure and in temperature, also infinitesimal in magnitude when we write that D. But G can also depend on other things. So let's say G depends not just on temperature and pressure, but also on the composition of the solution that's involved. So let N be the number of moles of some component. Let's identify the component as I. So we'll write N sub I. And then we can let I vary, as we'll look at in a little bit. But let's just consider I as a single component that the number of moles of which will affect the Gibbs free energy. As we pull I in or subtract it out of a solution, then that might affect the total Gibbs free energy of a system. So if it does, let's erase the chalkboard and write this over again. dG is equal to VdP minus SdT. But now we need some correction that takes care of the number of moles of I. So how do we do that? We're going to write something called a total differential. So if we have Gibbs free energy, or any function, doesn't matter what it is, let's say we have some function that is changing as a result of changes in pressure, temperature, and moles of I, the total differential can be written like this, where we take the partial differential, dG, with respect to, let's treat the first one, pressure, dP multiplied by dP plus the partial, we'll take this guy next, the partial, oops, that should be a Gibbs free energy with respect to temperature, and that's multiplied by dt, plus the change in Gibbs free energy with respect to the number of moles of I multiplied by dNi. We're using the partial symbol here, substituting that for d, because when we say that we have a partial derivative, it means we're holding other stuff constant. So over here, when we look at this, dg dp, we're holding the other variables, temperature and n sub I, constant. Pause the video for a second and try to guess at what we are holding constant here and here. So for the case of temperature, we're holding pressure and again, Ni constant, and over here it is pressure and temperature that are being held constant. Well, we already know what these are, right? This here is this, it's volume. So that's equal to volume. And we know that dG dt is S, or rather minus S. So we have dG is equal to V dP minus S dt. We've written this all several times already. And then plus this thing here. So what are we going to do with that? Well, we're going to make up a new symbol, mu sub I, and call it the chemical potential. And so we have the complete equation. Let's rewrite it a little more neatly. dG is equal to VdP minus SdT plus the chemical potential of I multiplied by the changes in I, the number of moles in I. So the chemical potential of I is dG dNi by definition. And it comes out of this idea of a total differential. Now, what if I is not the only thing that can vary? What if there are other moles of substances, a countable number of moles of, let's say, a J or a K, or et cetera? Or we could just number them, components 1, 2, 3, et cetera. Well, then we can add other terms. Over here, at the end of this equation, over here at the end of the equation, we can write plus mu sub j dnj, and plus mu sub k dnk. And we could do this until we run out of letters in the alphabet, or more precisely, when we run out of components in the solution that we're looking at that might affect the Gibbs free energy of the solution. Well, instead of writing all of these things individually, we can write it more generally by using summation notation. And so you'll usually see this written as VdP minus SdT plus the sum of all of the possible components. Let's just call them I. So mu I dNi. So here I is a stand-in for all of the possible components that might vary. Elements or compounds or mineral components where the sum of those would make up the sum of the solution that we're looking at. And that solution could be a magma, an aqueous solution, or a solid solution inside of a mineral. But that is our definition of a chemical potential. It is that corrective coefficient that tells us how the Gibbs free energy changes as a function of changing the composition of a system. And sometimes we write this in integral form where G over Ni is equal to mu sub I. So another way of writing this would be to say that mu of I well, of course, it's the chemical potential by definition, the way we set this up. It is also the partial molar Gibbs free energy. So the partial molar Gibbs free energy of a component I.